Have you ever noticed how a tiny push on a mechanic's foot pedal can lift an entire car? Or maybe thought about why a massive cargo ship just floats so easily on water while, a small stone sinks straight down? What about that distinct feeling of pressure when you dive just a few feet into a swimming pool?
Hmm.
Or even why cooking rice takes noticeably longer way up on a mountaintop? These aren't just like random things. They're governed by some really powerful, often unseen principles.
Exactly. And today we're taking a deep dive into that hidden world. It's all about the forces exerted by fluids when they're just sitting there, at rest. A fundamental area of physics known as pressure and fluid statics. Our mission for you today is really to cut through the complex stuff, give you a shortcut to being, genuinely well-informed on why things push and pull and balance in liquids and gases when they aren't actively flowing. You'll hopefully uncover those aha moments about things you see every day, equipping you not just with facts, but with a deeper feel for the world.
Yeah, and we've distilled this deep dive from, an incredibly detailed textbook chapter on pressure and fluid statics. It gave us some really fascinating insights to unpack for you, and we promise you don't need dense equations to really grasp these powerful concepts. Okay, so let's unpack the very foundation here. What exactly is pressure? At its heart, it's basically a normal force exerted by a fluid, right? Over a specific area. Think of it as how much a fluid pushes and pulls perpendicularly on a surface.
Right. And what's particularly interesting about fluid pressure, especially if you're familiar with stress in solids, is how different it is. Unlike a solid where stress can be very directional, pressure at any point in a static fluid is, the same in all directions. It's a scalar, not a vector. And while the official SI unit is the Pascal, that's newtons per square meter, it's often, a bit small for practical use. So we often see kilopascals or MPa, megapascals in engineering. You'll also commonly see units like bar, standard atmosphere, or even pounds force per square inch psi, especially like you said on a tire gauge. It really shows how context kind of dictates the most convenient unit to use.
That makes sense. So, okay, we've got pressure, but then you hear terms like absolute pressure, gauge pressure, and vacuum pressure.
Yeah.
What's the practical difference for us?
Well, most of us kind of get the idea of absolute pressure being measured relative to a perfect vacuum, absolute zero pressure. But the devices we use every day, like that tire gauge, they're usually set up to read zero at whatever the local atmospheric pressure is. That's your gauge pressure. So gauge pressure is basically just the difference between the absolute pressure and the air pressure around us. P gauge, pabs patamem. For instance, if your car tire gauge reads, say, 32.0 psi, that doesn't mean the absolute pressure inside is 32.0 psi. It means it's 32.0 psi above the surrounding atmospheric pressure. So if your local atmospheric pressure is maybe 14.3 psi, then the absolute pressure in that tire is actually 46.3 psi. And if a pressure is below atmospheric, we call that vacuum pressure. PVAC, patum pabnum. The key thing is always knowing your reference point.
Right, got it. That's a really useful distinction, and we definitely feel pressure changes, don't we? Divers especially know it changes with depth.
Yeah.
But how does this sort of vertical journey of pressure actually work?
Okay, so in a fluid at rest, you won't see pressure changing horizontally. Side to side, it's the same. But vertically, it increases linearly with depth. And the reason is pretty simple, really. It's just the increasing weight of the fluid column sitting above you. Imagine stacking layers of liquid. The deeper you go, the more layers are pressing down. So for a liquid open to the air, the gauge pressure at a depth is just That's density times gravity times height. Now, this brings up a good question. Why can we basically treat air pressure in a room as constant, top to bottom, but we absolutely can't do that with water pressure in, say, an ocean or even a pool?
That's a great point. I mean, I always just assume the air pressure is pretty much the same everywhere indoors.
Exactly. And you're generally right to do so. The huge difference is density. Gases have really, really low densities compared to liquids. So for small to moderate vertical distances, like the height of a room, the weight of that gas column is almost negligible, insignificant. Like the pressure change in a 5-meter high room, it's only about 0.006 atmospheres from the ceiling to the floor. You'd never notice it. But go down just a few meters in water, and the pressure change is significant. Any diver can tell you that.
Okay, here's where it gets, I think, really interesting. This brings us to Pascal's law. This is the idea behind so many things we use every day, right? Like hydraulic brakes, those car lifts at the garage, maybe even power steering.
Absolutely. Pascal's law is, well, it's a masterclass in force multiplication. It says that when you apply pressure to a fluid that's confined, that pressure increase gets transmitted equally instantly to every part of the fluid and the walls of the container. It's not just about car jacks, though. Pascal's law fundamentally frees us from needing to apply force directly. It lets us leverage huge power with just a little effort. Think about that tiny push on your brake pedal stopping a heavy car. So if you have two connected hydraulic cylinders, one small, one large, a small force on the small piston generates a proportionally much bigger force on the large piston. That's how you can lift, say, a 1,000-kilogram car with maybe just 10 kilograms of force if your hydraulic jack has an area ratio of 100. This principle, Simon Stevens demonstrated it way back in 1586, also tells us that pressure is the same at all points on a horizontal plane within a continuous static fluid. Doesn't matter what shape the container is. It's quite profound, really.
That's incredible. So a tiny force really can generate a massive one.
Right.
But wait, if the pressure itself is the same throughout the fluid, how does the force get magnified? Is it purely just the area difference? Or is there something else I'm missing?
Nope, you've got it. It is purely about the area difference. Remember, pressure equals force divided by area. So if the pressure is constant everywhere in that confined fluid, then a larger area simply translates that same pressure into a larger total force. F equals P times A. It's elegantly simple, but incredibly powerful in application.
Amazing. Okay, so we understand these powerful invisible forces now.
Yeah.
But how do we actually, measure them, put numbers to them? We've developed some really clever instruments, haven't we?
We certainly have. Maybe the most iconic one is the barometer, invented by Torricelli. It measures atmospheric pressure, typically using a column of mercury. And the height of that mercury column directly tells you the atmospheric pressure. Patium equals OK. To give you some perspective, a standard atmosphere supports a column of mercury that's 760 millimeters high. That's about 29.92 inches. Now, if we tried to use water instead of mercury, because mercury is so dense, well, you'd need a water column about 10.3 meters high, nearly 34 feet. Imagine a barometer that tall.
Whoa, that's quite a thought experiment. Hard to fit in the lab.
Exactly. And the fact that atmospheric pressure drops as you go higher has some really far-reaching effects. It's why water boils at lower temperatures at high altitudes, right? It makes your pasta or rice take longer to cook. It's also why nosebleeds can be more common in the mountains, bigger pressure difference across membranes, and why car engines produce less power, simply less air density, less oxygen getting into the cylinders. Airplanes, though, they use this to their advantage. They fly high because the air is less dense, which reduces drag and saves a lot of fuel.
Right, so barometers handle atmospheric pressure. But what if you need to know the pressure inside a sealed tank? Or maybe the difference in pressure between 2 points in a system? That's where manometers come in, right?
Absolutely. Manometers are fantastic for measuring those small to moderate pressure differences. They're usually simple U-shaped tubes, often filled with fluids like mercury or water or maybe oil. And they work using that same principle we keep coming back to pressure changing with depth, BPRL. If you have multiple layers of different fluids that don't mix, you just add or subtract those terms as you move vertically from a known pressure point, like the open end, to the point you want to measure. A really key insight here, something that makes solving manometer problems much easier, is that any 2 points at the same elevation within the same continuous fluid at rest will always be at the same pressure. That lets you kind of jump horizontally across the bottom of the U-tube or across any horizontal fluid layer. For instance, imagine a complex manometer measuring air pressure in a tank way up on a mountain. You could start from the open end, knowing the local atmospheric pressure, say 85.6 kPa at 1,400 meters altitude. Then you just work your way through the different fluid columns, maybe down through mercury, up through oil, down through water, adding and subtracting the clock for each section until you reach the air in the tank. And you might find the tank pressure is, say, 130 kPa.
Okay, that makes sense. Methodical. And beyond these fluid columns, we've developed even more sophisticated ways to measure pressure, too.
Oh, definitely. There's the classic Borden tube. That's a C-shaped or coiled metal tube that tends to straighten out when pressurized, and that movement is linked to a needle on a dial gauge. Very common. But for higher sensitivity, more precision, especially for electronic readouts, modern pressure transducers are really key. These devices convert pressure directly into an electrical signal. We're talking about things like strain gauge transducers, capacitance transducers, and piezoelectric transducers. Those are particularly interesting, discovered by the Curie brothers back in 1880. They actually generate an electric voltage when you apply mechanical pressure to certain crystals. And for the ultimate in precision, like for calibrating other gauges, there's the dead weight tester. It literally applies known weights to a piston of known area to generate a very precise pressure.
So, okay, we've defined pressure, we know how to measure it. But what about the actual forces these fluids exert on surfaces? I'm thinking about things like the face of a dam or the hull of a ship submerged in water.
Right, this is where fluid statics gets very tangible, dealing with forces. The resultant hydrostatic force on a flat, plane surface that's completely underwater is surprisingly simple to calculate conceptually. It's just the product of the pressure calculated at the geometric center, the centroid of that surface, multiplied by the total area of the surface. So FR excluding PCA. But here's the crucial bit. That resultant force doesn't actually act at the geometric center, the centroid. Because pressure increases the deeper you go, the force is weighted towards the bottom. So it acts at a point called the center of pressure, which is always below the centroid on a submerged vertical or inclined surface.
Okay, so it's not just pushing slap bang in the middle.
Yeah.
That makes sense because, yeah, the bottom of a dam wall experiences way more pressure than the top.
Precisely. And let's take a really dramatic example from the source material we looked at. A car door underwater. Imagine a car gets submerged in a lake. The door is maybe 1.2 meters high, 1 meter wide, and its top edge is 8 meters below the surface. The total hydrostatic force pushing on that door is calculated to be a staggering 101.3 kilonewtons. That's over 10 metric tons of force. Even a very strong person who can lift, say, 100 kilograms, that's about 1 kilonewton of force, they have absolutely no chance of opening that door against that pressure. The turning moment created by the water pressure is maybe 50 times what a person could generate trying to pull it open. This is why, in that awful situation, the driver's best bet, counterintuitively perhaps, is to let water into the car to equalize the pressure on both sides of the door before trying to open it. It's a terrifying thought, but a critical lesson in fluid forces.
Wow, yeah, terrifying is the right word, but really crucial to understand. Okay, so that's flat surfaces. What about forces on curved surfaces? That seems like it would be a much trickier calculation.
It is a bit more involved, yes, but the easiest way to think about it, conceptually, is usually to break the force down into horizontal and vertical components. The horizontal component of the force on the curved surface is actually equal to the force that would be on the flat vertical projection of that curved surface, like its shadow on a vertical wall. The vertical component, on the other hand, is equal to the force on the horizontal projection of the surface, plus or minus the weight of the actual block of fluid directly above or below the curved surface itself. You then combine the horizontal and vertical force components using vector addition to find the overall resultant force and its direction. A really neat insight, especially if the curve is part of a circle, is that the resultant hydrostatic force always passes through the center of that circle. That's because all the individual pressure forces are acting perpendicular or normal to the surface, and lines normal to a circle all point to its center.
Okay, this next part I think is where it gets really relatable for everyone. Buoyancy. You know, we all feel lighter when we're in the water. What's that sort of magical upward force all about?
Right, that's the buoyant force. It's the upward push exerted by a fluid on any object immersed in it. And it's caused directly by that pressure increase with depth we talked about. There's simply more upward pressure pushing on the bottom surfaces of an object than there is downward pressure pushing on its top surfaces. The famous Archimedes principle nails it. It states that this buoyant force is precisely equal to the weight of the fluid that the body displaces. And critically, this force acts upward through the centroid of that displaced volume of fluid, not necessarily the centroid of the object itself. What's really remarkable, and maybe counterintuitive, is that this buoyant force is completely independent of the object's own density or how deep it's submerged, as long as it's fully underwater. It's why, say, a 3-kilogram solid cube of copper and a 3-kilogram solid ball of copper, if both are fully submerged, experience the exact same buoyant force. They displace the same volume of water if they have the same mass and density, even though their shapes are different.
That is counterintuitive for some people, I bet. I think I always assumed the object's density played a role there directly.
Yeah, it's a common misconception for submerged objects. Now, for floating bodies, density is absolutely key. That's different. An object sinks if its average density is greater than the fluid's density. It floats if its average density is less than the fluid's. And it remains suspended, neutrally buoyant, if the densities are exactly equal. This means that the fraction of a floating object's volume that's submerged is simply the ratio of its average density to the fluid's density. And while we often ignore it for ourselves walking around, buoyancy in gases is super important for things like hot air balloons. The balloon floats because the warm air inside is less dense than the cooler air outside, creating enough buoyant force to lift the balloon and its payload. It's also behind natural convection currents in a room. A typical person actually experiences a buoyant force of about 1.2 newtons from the air around them. That's totally negligible compared to, say, an 80-kilogram person's weight of 788 newtons. But for a balloon, that air buoyancy is absolutely everything.
Okay, so floating is one thing, but beyond just floating, there's the whole concept of stability. How do we know if something, like a ship, will stay upright or if it's likely to tip over? That seems vital.
Absolutely vital. We can think about stability using a simple analogy like a ball on the floor. If you nudge it and it returns to its spot, it's stable. If it stays where you nudged it, it's neutrally stable. If it rolls away and keeps going, it's unstable. Now, for bodies completely immersed in a fluid like a submarine, they're usually vertically stable. Push it down, the buoyant force brings it back up slightly, push it up, gravity pulls it down. Rotational stability is the main concern. An immersed body is rotationally stable if its center of gravity, G, is directly below its center of buoyancy, B, which is the center of the displaced volume. Think about why a submarine has its heavy engines and ballast low down, or why a hot air balloon carries its basket and passengers at the very bottom. It keeps G below B. If the center of gravity happens to be above the center of buoyancy, the object is unstable and will tend to flip over to reach a stable state.
So for submarines and balloons, keep the weight low. Got it.
Exactly. Now, for floating bodies, like ships, it's actually a bit more nuanced and interesting. Even if the ship's center of gravity G is above its center of buoyancy B, which is often the case, it can still be perfectly stable. This is because as a stable ship starts to tilt or list, the shape of the underwater volume changes. This causes the center of buoyancy B to shift sideways. This shift creates a restoring moment, a torque that tends to push the ship back upright. We measure this tendency using something called the metacentric height. That's the distance between the center of gravity G and a point called the metacenter, M. The metacenter is the point where a vertical line through the new center of buoyancy, when tilted, intersects the original center line. If the metacenter M is above the center of gravity G, the ship is stable. The larger this distance, the metacentric height GM, the more stable the ship is, the quicker it rights itself.
Okay, that's fascinating. Stability for floating things is more complex than just keeping the weight low. Now, we've mostly talked about fluid statics, fluids at rest. But what if the whole chunk of fluid is moving together, like accelerating in a truck or spinning in a centrifuge, but without any internal sloshing or shear between the fluid layers? This is that realm of fluid, rigid body motion, isn't it?
That's exactly right. It happens when a fluid that's maybe in a container moves as if it were a solid block. Every single particle in the fluid has the same acceleration vector. For simple linear acceleration, like a tank of water on an accelerating truck, the free surface of the liquid doesn't stay flat. It actually tilts and becomes an inclined plane. This raises a fun practical question for you. Imagine you're transporting a fish tank on a truck. The truck accelerates from 0 to 90 kilometers per hour in 10 seconds. The tank is, say, 80 centimeters high. Which way should you orient the tank in the truck bed to minimize the chance of water spilling out? Long side parallel to the motion or short side?
Okay, my first thought is give it more room. So put the long side parallel to the acceleration. But based on the physics, maybe intuition is wrong here.
Yeah, that's a common first thought, but actually you should definitely orient the tank with its short side parallel to the direction of motion. In the example you gave with that acceleration, if the long side were parallel to the motion, the water level at the back could rise by maybe 25.5 centimeters, which might well cause a spill in an 80-centimeter high tank. But if you turn it so the short side is parallel to the motion, the water rise at the back would only be about 7.6 centimeters. Much safer. It all comes down to the angle the surface makes, which depends on the acceleration. For a given angle, a shorter length means a smaller vertical rise at the back.
That's a fantastic aha moment right there. So shorter is actually better for stability during acceleration. Fascinating. And what happens when you rotate a container of liquid, like spinning a glass of water, but maybe faster?
That's called forced vortex motion. When you spin a container, the liquid inside is forced outwards due to, well, effectively centripetal acceleration needing a pressure gradient. And the free surface is no longer flat. It takes on the very distinct shape of a paraboloid of revolution like a satellite dish. The faster you spin it, the deeper the dip in the center becomes and the higher the liquid climbs up the edges. This isn't just a cool visual. This principle is actually used to create incredibly precise mirrors for telescopes. They spin a container of liquid mercury, and the perfectly parabolic surface that forms naturally is used as the primary mirror. To give you a practical feel for it, if you had a cylindrical container, maybe 60 centimeters high and 20 centimeters in diameter, filled with liquid up to 50 centimeters, if you start rotating it, the liquid would just begin to spill over the top edge when the rotational speed hits about 19.8 radians per second. That's roughly 189 revolutions per minute. And at that exact speed, the center of the liquid surface would have dropped down by 10 centimeters to the 40 centimeter mark, while the edges climbed 10 centimeters to reach the 60 centimeter top rim.
Wow, that gives a really clear visual of the effect.
Huh.
Okay, we have covered so much ground today. From the fundamental definition of pressure and why we use so many different units for it, to how it changes with depth, and all those clever devices we use to measure it, we explored the really powerful forces fluids exert on submerged surfaces, flat and curved, understood the science behind why things float or sink or stay stable, and even dipped into how fluids behave when they're accelerating or rotating like a solid block. It's been quite a journey through these hidden forces.
Yeah, our goal was really to give you a clear, kind of structured understanding of fluid statics, connecting what can feel like dense physics concepts to practical, hopefully memorable examples you see all around you. Hopefully you've had a few of those aha moments about the everyday world, from how car jacks work to why hot air balloons manage to fly.
Absolutely. And I think this raises an important question for you, the listener, to ponder. Now that you understand these foundational principles of fluid statics, what other seemingly simple hidden forces in your daily life are you now curious to maybe explore next?
Yeah, take a moment next time you see water in a glass or check your tire pressure or even just go for a swim. What seemingly simple interaction might actually be a really complex dance of pressure and forces? And how might understanding these principles maybe change the way you interact with or just appreciate these everyday objects and phenomena?